Code to the cloud. Yeah, sick. All right, so welcome everyone. This is a presentation I gave last year for MUGS as well. Basically, the kind of motivation for it is to get you guys understanding why learning SolidWorks properly is a good thing to do for starters, and number two, why having some experience with CAD anyway is a really important thing to develop, particularly in mechanical engineering. So we're going to be going through getting you interested in SolidWorks for a start, helping you understand why you need to know CAD in the first place. Then I'll be going through some of the basics and giving you some pointers to get you feeling confident in using CAD going forward. So I suppose for starters, what's so good about SolidWorks? Why do we use it? Why do we use SolidWorks over other forms of software? SolidWorks is a pretty good industry standard software for mech design. It's got some good inbuilt simulation and good interfacing with other packages as well. There's also a project management framework inbuilt to it as well. So SolidWorks is pretty widely used in that regard for doing CAD out in the workforce. Just check chat. Cool. So with SolidWorks, you're able to produce not only 3D parts, but also 2D engineering drawings. And that's pretty important in order to be able to make things, most manufacturers work off the 2D drawings. There's lots of toolboxes for plastics, sheet metal, computer-aided manufacturing, electrical routing, pipes, and all that other funky stuff that is quite, I suppose, hard to do by hand. So having a CAD program to do it for you is a really nice way of doing it. I'd say it's probably one of the most versatile general CAD programs out there, but there's certainly some more sort of specialized ones as well that are worth looking into. The other thing as well is it opens up a whole new world of computational engineering. So here we've got, for example, a part that I've made in SolidWorks, and then I've taken it over to a program called ANSYS that you'll end up learning in future years in engineering. And in this particular case, it's showing off a modal deformation, I suppose, plot, but you can have it do all sorts of other things as well. One of which is topology optimization, which is a really kind of key and up and coming area. And it's based on this idea of you start off with an original design and then you use optimization methods to go through and tear little bits of it off that aren't really helping the structural integrity of it. In this particular case, we have a funny angle bracket here with two holes in it. We load it with some forces on these 2 points. We run it through ANSYS and it goes through and it actually generates a whole new model for us. So being able to design something rough initially, chuck it into one of these programs and then have it spit out a new model for us to use that we can then re-interface with other parts is actually quite important. And it's definitely where mechanical engineering is kind of progressing towards in terms of actual product design and manufacture. Okay, so that's kind of a broad overview about what SolidWorks can do, why it interfaces with other parts really well, and why that's kind of important. The next thing that we actually move into, and this is kind of the core section of this presentation, is looking at what SolidWorks actually does to be able to build up a model. Having a fundamental understanding of this is actually a pretty key thing, and it will help you generate models going forward. So this idea of additive versus subtractive modeling. So it's this idea of, in order to build up a model, do we add bits of material to it or do we subtract that material? And this is quite important when you're looking to build parts that actually need to be manufactured. And the reason why it's important is the manufacturing techniques that we actually use in the real world look at both of these things. So for example, 3D printing is an additive process. We have a bed that moves around and a nozzle deposits bits of material. So it actually adds up to be able to build a structure. Milling, on the other hand, is subtractive. You start off with a chunk of metal, it goes around with a cutter, and gets rid of that material. Having an understanding of how those two are different and specifically targeting your design for one or the other can make it like a whole lot easier to actually generate those parts. In practice though, you can't just use one or the other. When you're building parts up, you'll probably need to use a combination. So if you have internal features, which are quite common, you will end up needing to use both additive and subtractive modeling. But understanding which has strengths in what area is kind of important too. The reason I bring this up is SolidWorks is actually built for this. So if you look at the screen of SolidWorks, the very first thing that pops up is this Features tab. And this actually is split between two things, additive features and subtractive features. Everything on this side here is looking at building up material, and everything on this side over here is looking at cutting material off. So having this kind of knowledge that, wow, SolidWorks is actually doing this in the background, and that's how you should be subconsciously thinking, is really quite important, I think. So we're going to consider this in a bit of an exercise. Here's a part that I've generated here that you can actually build in two ways, one of which by subtractive modeling, the other one by additive modeling. So this funny looking thing here, okay, we have a block that's 80 by 60. It's got some holes that are sequentially drilled into it, and they're all co-centered up here. I'm not sure how familiar you guys are with reading engineering drawings, so I'm going to talk through kind of my mindset when I look at something like this. Each of these are concentric. The bottom one is the thinnest at 20 millimeters, and it opens out up to 40 millimeters diameter as we go up here. And they're obviously at different heights. So when I look at this, I can kind of see that there's two ways that I could generate this. The first way I could do it would be purely additive. And what I would do there is I would start off with a plane on the bottom. I'd build up this first layer here with that one hole in it up to 20 centimeters. Then I would start drawing on that next surface, another rectangle with a hole in the center of it that's slightly larger, build that up to the next layer, and then build the third layer on top of that. That would be totally additive. I haven't done any subtractive processes. The issue there, of course, is that's kind of an unintuitive way to do it. The other way you could do it is you start off with a block, and this is the way that you probably would go about doing it. Start off with a block that's 80 by 60, and then you start subtracting out progressively these circles, going down with thinner and thinner diameters. And that would be a subtractive modeling approach to it. Obviously, that's probably much more natural to you. That's the way that, if you wanted to build this in the real world, that's the way you do it. You have a block of metal, you drill progressively down to take the material out. But yeah, that kind of just shows, the two approaches that I'm talking about here, additive and subtractive modeling. Another key thing that you should be thinking about is, okay, well, what do I need to consider before I go about actually starting a model? Where do I start with this? So the first thing I would say that you should do is you should make a bit of a game plan as to how you're going to approach it, how you're going to start building it up and getting to that sort of final product. So do you want to start with a block and remove material as we did in the previous example, or start with a base sketch and build things onto it? They're kind of the things that you should be considering. The other thing that you want to do is kind of get a bit of an idea for the proportions of the part. So you'll have a drawing in front of you. It might have a range of holes in it and fillets and all sorts of other things, but getting an idea for how big they should actually be in relation to the other parts is quite important as well. It gives you kind of this intuitive check as to whether you're actually building, what you're actually building is indicative of the real thing. The other thing that you should do as well, and this is something I want to stress, is you should look for symmetry in your part. CAD programs allow you to mirror things, and this makes your job much, much easier than it would be having to go through and build everything in a model. If you can see a line of symmetry in your part, well, that's going to be a whole lot easier for you to actually build up. Okay, so now I'm going to move on to the next section, which is talking about parts. So parts are kind of the individual components in SolidWorks, and we make a sequence of parts. We can then put them together in an assembly. So a brief overview. In order to cut or extrude anything, we need a sketch that is on a plane or a surface. So a surface on a pre-existing model or a plane that we've generated. So that might be top, bottom, left, side, whatever. You're able to mirror features and sketches or rotate them around an axis. And this is something that you should keep in your mind, as I said. It makes your job a whole lot easier. It means you only need to dimension something once and then rely on the symmetry to be able to place it. The other thing you want to do is you want to minimize the amount of features you need to sketch individually. So if you're able to generate a sequence of features in a sketch and then extrude up, that's going to be a whole lot easier than starting extruding. Okay, now I need to cut these bits off. Okay, now I need to extrude this a bit out. Pre-planning in this case, is kind of key. The other thing is when you have holes in your parts, you want to use the hole wizard wherever possible. And the reason for this is SolidWorks is able to fill those holes in with screws and bolts. And that makes your job a whole lot easier. If you go through and want to generate a bill of materials for your part, it can actually put in how many screws you want in the end. And it just makes it a lot easier when you go to building assemblies, having it kind of rooted in the real world with what the fixtures you would use would be. So we want to create features in our part using sketches. So what I mean here is, as I showed before, these sorts of features, either additive, subtractive, or combination, using these sketch entities. And this is kind of just like basic geometry. So we're building up these 3D features using 2D basic geometry. Something that's quite key that I think anyone that is new to SolidWorks should be aware of is this concept of reference geometry. This is here to make your job a hell of a lot easier. It basically allows you to start creating features off of surfaces to join later. So you can apply geometrical constraints and use them as your kind of baseline. So you can create a plane that's 10 mil off a surface and start sketching on that to extrude down, for example. The other really good thing is this idea of construction geometry as well. So when you're in a sketch, you start drawing up the geometry that you actually want to use as a component of that sketch, but you can also lay out other parts of geometry that is just there to help you construct and place things as well. Now, what do I mean by that? Well, these could be 3 holes on a square part, each a radius from one of the corners. So in this case, I have my 3 holes here. I've drawn them and you can see that they're this solid black color. And that indicates that they're actual sketch features. But I've also then clicked on my arc here that I've drawn from this point at a radius. And I've clicked this box called for construction. Now, what this means is when I go through and start doing either extruding or cutting these holes, they're the only things that SolidWorks will actually see as features for the part. It'll ignore having to cut through that line or whatever. That for construction line is just for construction. It doesn't actually go through to the real part. So being aware of that and using that to your advantage is quite important. You can see that a lot of the constraints that I've put here, I'm able to fully constrain this middle circle by only dimensioning these 2 outer circles. And I talk about what fully constrained sketch geometry looks like in a moment's time. The other thing you can do is rather than just having a 2D piece of, a 1D piece of geometry, as I had in that arc before, you can have a 2D piece of geometry. So in this case, I've actually put a plane that is tangent to these two holes in my plate, but cuts through this third one. And how have I done that? Well, I've said to SolidWorks, I want to input a plane here. I want it to be tangent to the first one, and it goes, okay, cool. And then it goes, all right, where's the second reference, the second face of this hole? It's also tangent there. And so it can fully constrain that plane to be tangent to both of those. And that's kind of an indication of a more 3D version of construction geometry, reference geometry rather. I mentioned a moment ago about sketches needing to be fully constrained. Now, what do I mean by this? Well, SolidWorks is only able to do what you tell it to do. If it doesn't have enough information, well, it's not really sure where you want to place something. So there's three types of sketch definitions. There's undefined, which is when something is blue. There's fully defined, which is when it goes black. And there's overdefined. And there's two sorts of overdefined. Red, which is unsolvable. You've given sets of geometry to SolidWorks that it just can't solve, and yellow, which is overconstrained. So, I mean, an indication of overconstrained that I have on the screen here is a rectangle that I've put in. I've dimensioned both its sides, but then I've dimensioned this diagonal. And so it's not really sure which one it should pay attention to, whether it should look at this top side here or the diagonal in that case. And the good thing is, because they're different colors, you can work out where they are pretty easily and go about correcting them by deleting dimensions or adding new ones in to fully define. Another thing is geometrical relations. And we'll get to this when we do an example in a second. Now, geometrical relations are inside of a sketch part, and they indicated by these little green boxes here. These are really, really handy, and it allows you to relate parts of geometry in your sketch to one another. So in this case, these lines here, this vertical line has a symbol that it's vertical. This horizontal line has a symbol that it's horizontal. And what that means is SolidWorks knows that that line is constrained to that horizontal fashion or that vertical fashion. You can also add things like coincident, where you have a line intersect another curve. It creates a point that is coincident on that curve. You've then also got tangent constraints. So you have a line that is tangent to a circle. And you've also got things that SolidWorks might generate automatically for you here, like a midpoint constraint. So if you click to put a line between the center point of this edge and that circle, it'll add a midpoint constraint automatically, and also things here like a rotational symmetry. So there's quite a few of those inbuilt, and they're really, really handy. We'll kind of show them off in a second. I'll post the link to this in here once again. This is in the exercises on that page. There's a PDF there. We're going to actually go through, and I'm going to give a live demonstration of how we actually would go about making a part by looking at some of these constraints. And you guys are welcome to follow along in the background as well. So just give me a moment to exit out of that and bring up my dimensions on this screen. So I suppose first thing to do is to look at what the actual drawing is showing us here. Okay, so we've got this funny looking part. We've noticed that there's a number of dimensions here. So when I'm talking about pre-planning, I'm thinking, okay, that's probably a good base point to center everything to start off from. That's probably a good place to start because I know that I can constrain a number of my features around that. We've also got this funny bump on top that looks like it needs to be constrained from the horizontal side. So, okay, I probably need to put in some reference geometry to be able to do that, probably in the form of a vertical plane. that I offset. And that's obviously got a radius that corresponds to that width. So that's something to be aware of as well. And a couple of fillets as well around the part. So these are all things that you've got to be aware of. But I think this center point here is definitely a good place to start. And I notice that this entire profile I can probably do in one sketch entity. I don't need to go through and do multiple sorts of features. So, okay, let's have a go at that now. I've already got that center circle put into place. And I note that that's going to be a diameter of 31.5, like so. And wait for this to load. Okay, 31.5. All right, so there's that first circle in. The next thing I want to do is I want to put another circle around it, and that corresponds to the wider part of that chain link. So let's go ahead and add another circle in. Now this one, it says a radius dimension, and I can dimension for a radius dimension from here out to there, like so. Oh, interesting. Won't let me. It's all right. It's okay. We'll click off the circle once more. Okay, that's worked that time. You'll probably hear that, or you'll probably see that I'm not actually clicking this dimension button. In my case, what I've done is I've bound the dimension button to the D key on my keyboard, which I think is quite an intuitive thing to do. But it's certainly something that, yeah, personal preference. You can keep clicking up to the dimension in your case. So in this case, that circle has a radius of 31.25. So times that by 2, that's going to be 62.5. Last time I did maths. Wait for that to load. And the next thing we want to be looking at is that top horizontal line. So we'll click the line. Now we know that's going to be tangent. So I want to come down here. I'm going to click the top of my circle and create a horizontal line like so. That's going to come across. And then I also want another line that's beneath it. Let's go about, and this one is not going to be, it's not going to be tangent. It's going to be horizontal. So this is where we might want to add in one of our constraints. And you'll see that SolidWorks is clicking here to that horizontal constraint. If it doesn't, you can always go over to the side and click on the line and add in that horizontal relation. But in this case, it's done it for me. So, okay, that's our that's kind of our left section almost done, not quite there yet. The next thing we want to do is we want to look at starting to get the circle going on the other side over here. So let's draw a circle. Our inner circle is going to be a diameter of 31.25 again. We'll come down, dimension that, 31.25. And again, it's also got a radius of 31.25 as well. So we can go through and add our external circle. Now you notice I haven't joined this up yet. And again, this is where applying our different constraints is going to come in quite handy. Click that, make that 62.5 once more. Okay. So what we need to do here is we need to make it so those two are tangent to one another. So what I've done is I've selected the outside of this circle, I've held Control, and I've selected this line. This gives me the ability to add some geometrical relations, as I was talking about earlier, to both of these sketch entities. So if I click tangent, you'll see that this is now clicked down so that that line is now tangent. What we now want to do is we want to drag this such that it's coincident onto that curve, which is just done there. We also want to drag this one across a little more, and that will also add in a coincident constraint. So, okay, this is now taking shape. The next thing we want to do is we want to dimension where the center of this circle is relative to this first one. So let's go ahead and do that. I want to click the center of this circle and the center of this circle, like so. And that gives me a dimension between those two. And I should now be able to edit that dimension, which in this case is 131.5 millimeters. All right, that's now brought that in slightly. The next thing we want to look at is adding in the radius between my left hand on the top, between my left hand circle here and this line, and between my bottom line and my curve here. So I think from memory, the way we go about doing that is adding in a sketch fillet. And I want to hold Control, Enter, or click between these two. Oh, hang on, no. I think I need to click this. Oh, great. That's all right. We'll add the fillets later. The next thing we want to do is apply the width here, which is a radius of 18.75 times 2, which handy thing to have is a calculator, of course. 18.75 times 2, 37.5. And okay, we've now got our rough shape pretty much, bar our fillets there, but I think I can do them later. Okay, the next thing we can do is we can trim some unnecessary parts here, and that gives us the rough shape of our linkage. All right, so now we've made our sketch. The next thing we want to do is we want to go through and make this into a feature. And so in order to do that, I'm going to be extruding it. So building up my part. I open this. It's already selected the largest area for me, which is nice. And I want to extrude that blindly up by 25 millimeters. So that's doing that just there. Okay, so now we've got our linkage there. I'll try and add those fillets in for the moment. So they're 25 millimeters, I believe. I can, yep, click that line in there, and then this line in here. And that's going to add in both of those curves, like so. The next thing we want to do is we want to add that funny bump on top of our linkage. Now, in order to do that, this is where we're going to need to use some reference geometry. So let me just rearrange my view slightly. In order to add in reference geometry, we come up top here, we click plane in our case. Now, I kind of made this easy on myself because I chose to start that first hole at the origin of my part. So what that means is that my right plane actually cuts through my part, which is quite nice. So in this case, I need to make sure that my little bump is 56.25 millimeters in that direction. So what I can do is I can basically put a plane there that I can start drawing on. So in this case, 56.25. This is currently going in the opposite direction. What I can do is I can flip that offset and it will put a plane in the very center of my part, right where that bump needs to be. Okay, let's add that plane there. So our plane sitting there nicely, make that a little larger. Then the only thing we need to do now is we need to add a semicircle. So we're going to click sketch, and I clicked on the plane before, and that means that my sketch is automatically entered to be on that plane. And now I can switch to an end view, sit over here, and just add in a semicircle. So the way I'm going to do that is I'm not going to do a center point arc. I think I'm going to do a tangent arc. I'm going to click here. Oh. Actually, let's do it via a circle. That might be slightly easier. Oh, why is that? Okay, now we've got a circle. Cool. Draw that out like so. Now, in order to dimension it, select that end part once more. And you notice that it's slightly off. So what we can do is we can add some constraints in. I'm going to click the outside of my circle. Then I want to click this line of my part, hit Control. And the other thing you need to do is click this surface and do what's known as convert entities. And what that does is it takes, oh, that's annoying. I said to Nick before that it would get up to this point and things wouldn't work for me. That's all right. I know what this needs to be. That needs to be a radius of 18.75. So if it's a radius of 18.75, it's a diameter of 37.5. Like so. We can put in a line that goes from this edge here using a coincident constraint over to this other edge here, like so. Click that point and that line and add a pierce constraint, and that's now fully constrained. So my semicircle is now sitting where it needs to be. The next thing we can do, trim the bottom of our semicircle because we don't need it anymore. So go to trim entities, go there, and our sketch is now over defined. Okay. So that's all good. We can just remove that dimension like so. And now our sketch is happy. And you'll notice that we've defined that now without actually having to add any dimensions in. So, okay, what's the last thing we need to do now? Is we need to extrude it. That's going towards this end here. We don't want that. We want that to go in the other direction. So we're going to click this reverse direction button, and we'll note that it's 18.75 millimeters long. Okay, click OK there. that should generate nicely, like so. Very good. That plane, we're now done. We don't need it anymore. So we can actually hide that. So if you click on it, mouse over your plane, there's a button here that says hide. Click that and it'll go away. The very last thing we need to do is we need to add a 3mm fillet to the sides of our little bump here. So we go up the top, we click fillet, and we now want to fillet these two edges. And just like so, cool. So we're going to add in 3mm because that's how long our fillet is going to be. And we then want to click these two edges like so. And that should be us done. The last thing you always want to do is you want to compare it with your drawing. So in this case, there's our part, there's our drawing, and that looks pretty good to me. And what this says is we've gone through and we've reconstructed it to the best of our abilities from all these dimensions in 3D. So that is kind of how I would go about making a part. It was probably long and tedious, but I think it's quite logical, particularly if you're just beginning with CAD, to see how someone goes about approaching a part and building it up from scratch. So we are not going to do the second part because, as usual, it takes a lot longer than I expect. Let me just swap these two around. The next thing we are going to do, though, is we are going to look at assemblies. Well, I suppose the last thing I want to talk about is that was building something in 3D. Obviously, when you build up a model, you probably want to produce a 2D model of that as well. And so how do you do that? You go up the very top of your screen and there's a button that says make drawing from part or assembly. And that then takes you into SolidWorks' 2D drawing suite. So that allows you to create a drawing from your part such that you could give it to someone else and they can take the dimensions and try and recreate it for themselves. The good thing about SolidWorks is you don't need to type all the dimensions out again. They're already stored in the model. So when you go through and you dimension something in a drawing, it's actually drawing those dimensions from your initial part, like so. And this is how designs are interpreted in the industry, right? Basically requires a whole undergrad unit on how to understand how you generate these drawings, which is what Mech 2400 is. And it's quite important that you understand how you can take things then from 3D to 2D to then have someone build a 3D part for you. Okay, so the next part of this seminar is looking at assemblies. So we've generated a part. Now what do we do with it? Essentially, parts can fit together into a final product called an assembly, and this allows us to virtually reconstruct the part. It allows us to see how it fits together in a 3D model. We can check things like tolerances and interferences and whether we've actually modeled it correctly. And then we can also do some fancier stuff as well, like performing motion studies. So the good thing is it's basically like Lego. Each part is a block. There's mates in an assembly that allow us to push them together and hold them in place. We can add pins for bearings and joints, and we can basically play with our design as we go along to make sure it all fits. So those mates I was talking about, these kind of constrain your design. So it places either a range of limits on the placement of surfaces, edges, or points, or it imposes hard constraints. So things need to be located where you describe them to be. It can also be used to generate some mechanical constraints. So these are these ones sitting over here on the side. So that's where if you actually have a model that you want to see working in real life in SolidWorks, you can add those in and have it move as it would in the real world. So this is what we're going to be making today. It's a clamp, and the way it kind of functions is like this. And this is all generated in SolidWorks. So we have a lever arm. We have here some pins that we're going to be hinging off and using as bearing joints. We've also then got this funny bit at the end, which holds the part that actually clamps. But you can see that this is kind of a relatively complex mechanism, but you'll realize that it's pretty easy to put together in SolidWorks, which is quite nice. So, okay, how are we going to go about doing this? Well, on that website, should be in the chat still. If not, I'll add it again. There's a link to download the assembly files. What you want to do is you want to unzip the folder, open the clamp unassembled file in that folder, and that's got all the parts already sitting in there. So you don't need to import them. All that we need to do is assemble them together. So I'll give you guys a second just to look into that and make sure you've got it opened. In the meantime, you can look at this very nice rendering of this clamp, like so. I'll give you guys maybe 20 more seconds to get that opened and ready. And I will also go through and open my clamp unassembled. Okay. So here are all our parts. They're all sitting in there nice and ready for us. So how do we go about putting it together? Well, again, like with a part, you kind of need to have a plan for how you're going to go about doing this. So when I look at my diagram of how this fits together, I can see that we have some pins in this bottom bit for starters. We then have pins in our handle, and then these sheet metal parts kind of slip over the top. So that's how you go about doing it in real life as well, right? So all we need to do is replicate doing that in SolidWorks. So how do we do that? Okay, we go to the Assembly tab, we click Mate, and we can go through and add some of these pins. So I want this larger part of the pin to sit inside this hole, and SolidWorks is going to move it over there and slot it in that hole for me. The next thing we want to do is we want to make sure that this end surface is flush with this surface here. And SolidWorks has gone and automatically done that for us as well. So we just need to now keep going, keep putting our pins inside, and make sure you click on the surfaces. If you don't, you come over to the mate selections, just hit delete on your keyboard, then re-click in the box and click a new surface. And that's now our second pin in our base. All right, the next thing we want to do is want to add these in the handle as well. Like so. Make this flush, and make those two coincident. Add this in. Okay. Add that, mate that. All right. And now all our pins are inserted. All right. The next thing we want to do is these two bits here, these kind of side mechanical linkages, they look to sit over the top of our pins down here. So let's go put them in next. So I suppose we know that they're going to be flush with this side here. So we can go through and make sure that those two stick together. And the next thing we want to do is we want to make sure that the linkage hole lines up with this part of our pin. So we can go through, add a constraint there, and that's sitting where we want it to. We then want to append this other one, obviously, to the other side. Click over there. We then want to go through, make sure the holes line up. So click the hole, click our pin. They're now in the right place. Kind of a key thing that you should consider at this point, and I'll just exit out of the mate menu for a moment, is that these two parts of the linkage aren't currently joined together. So they can move independently of one another. This will be quite a common thing when you're working with some relatively complex assemblies. And so the way you go about fixing that is you add a constraint between some of your moving parts as well. So to kind of show that off, I can move this linkage, and you'll notice that the other linkage behind it isn't really moving at the same time. That's all good. Let's add a mate between these two back edges of our linkages. I really hope my computer isn't freezing. I am just going to exit out of that real quick. Okay, cool. Switch over to SolidWorks. All right, we now have our mate menu up, our mate selections. We're going to click these two parts. Such that they're coincident, which is good. All right, the next thing we want to do is we've obviously got those side linkages in. We probably want to now constrain our clampy bit onto the end. So how do we do that? Well, as we've done before, click inside one of our holes and click on our pin. And you really do get the feeling now that this is exactly like Lego, right? It's pretty much just taking your bits and pieces, adding them together and making sure everything is well constrained. So, okay, that's now sitting coincident. You notice that we have two holes here. There's really no need for constraining this other side concentrically as well. But what we do want to do is we want to constrain the side part of this toggle bar so that it sits flush with the outside of our base part, like so. All right, that's now in. The next thing for us to do is to finally add on our handle. So we need to make sure that we're getting this the right way around. Let me just zoom out. Okay, so the really long part of the handle needs to sit over on this end. So that means that this pin needs to fit in these holes here. So we go through, we click our pin and align it. In this case, it looks like our mate is going to be misaligned. So this is quite a common thing. It's no worries. All you need to do is click the mate alignment and it will flip your part around to rearrange that mate. So, okay, those two are now concentric. I can accept that mate. The next thing we want to do is slide this over so it sits in between here. So we're going to do that by clicking this side and then clicking the inside of these linkages, like so. And this will shift it over so it sits in nicely there. And the last thing, the very last step, is to make sure that this pin fits inside our clampy bit at the end. So that's not a problem. We just click and click again. And that should be our mate, our part fully constrained. So, okay, very good. We can exit out of the mate menu. And we can actually actuate this in the assembly, and you can see how it operates. So how do we do that? Well, we grab the end of the handle, obviously, and we can move it around. And we can see that this is now working much like the video I showed you earlier. So that's good. It means we've assembled it correctly. Nothing's breaking. We haven't fully constrained this. And this is kind of more of an advanced type thing that you might do in industry. You see that my handle actually passes through. You can add things like angle constraints so that this won't do that. And you can add mechanical constraints so that this handle will actually physically interfere with this base part. But we don't have time to do that today, unfortunately. I'll leave it as an exercise to the reader, as they say. Cool. So that's the assembly all done. You can try that in your own time, or complete that in your own time rather, as I am conscious of the clock. The last kind of little thing, and I've added this in for this year, is how you would actually go about manufacturing a part that you've made. And this is quite, I suppose, a relevant thing. So you've designed a part, cool. How do you actually use that? Well, SolidWorks stores that info in their own format, the solid part format. Some software can extract that information, so ANSYS can, others can't. So you need to actually convert your files. There's a couple of widely used formats. Probably the most relevant or the most widely used is what's known as an STL file, a stereolithography file, or a standard triangle language, depending on who you talk to. So what do I mean by this? Well, pretty easy. In order to export something for 3D printing, all you need to do is save your part as an STL file. So in this case, if you save as, it'll try and save it as a SolidWorks part, .prt or a .sld PRT. But if you scroll down, there's an STL option for you, like so. You might see in some softwares that an IGES or a step file is also used. They're very similar ways of expressing the information and pretty open source as well. A less common one, but probably useful to know as well, is a PLY file. And these are used in computer graphics as well. So you could actually make something in SolidWorks, export it as a PLY file, and then have it in a computer game or a simulation or something as well. So you have that STL file. What do you do with it? Well, there's a thing called Cura. It's a piece of free software. I use it for my 3D printer at home. You basically just drag and drop in your STLs, load in your printer config, and then hit this big blue button down the bottom. And that slices it up into a whole bunch of little slices that you can then send to a 3D printer. And hey presto, you can manufacture parts very, very easily that you've designed in SolidWorks. This last little part of this seminar is, where do you go next with SolidWorks? Well, SolidWorks is pretty good at what it does, and I hope you guys recognize that now. You're able to successfully take a 2D engineering drawing and transfer that into a 3D part, which you could then send for 3D printing or machining. Knowing this much SolidWorks would probably get you by for the first, I suppose, couple of forays into that space. But it also kind of begins to open doors for you in some other things. So things like simulations, computational fluid dynamics around the outside of structures, topology optimization, like I showed some examples for earlier, and some more complex things like electrical routing and pipe work that is regularly done in industry. And hopefully as well, this has opened your eyes to a bit of design engineering work as well. something I want you guys to take away is design engineering is not everyone's favorite thing. You don't have to be a design engineer, but I really do think you should be able to communicate designs. Communication's pretty key, and engineers usually like to communicate things visually. So making drawings of parts and then sending that off for manufacturer. The best engineers draw to a standard that everyone can understand, and whether they're trying to communicate with other engineers, workmen, or the public, drawings are a pretty good way of doing that. You also never know when you'll need it. So if you end up owning a 3D printer in the future, being able to actually make your own parts is a pretty useful thing as well. You can fix things around the house if you so wanted to. Some suggestions for you. If you think you're going to use SolidWorks at least once in a blue moon, I do recommend the following: dual monitors. So I've got a big one sitting here in front of me that all your faces are on, and also this one, my main computer screen that I've been SolidWorksing off of. Makes it a hell of a lot easier because you can have your drawing on one and you can have your actual part and assembly on the other. The other thing is a good mouse. So I've got a Logitech MX Master 2 or whatever, which is pretty nice and ergonomic design, and being able to click using a mouse is a whole lot easier, as well as being able to scroll in and orbit around parts as well. And the other thing is either a set of calipers or a micrometer. That there's some pictures of there. The reason I recommend these is, if you have physical objects in the real world and you want to make models of them, well, you need something to be able to transfer that physical objects into a set of dimensions that you can then enter into SolidWorks to build those models up. And they're also handy to have. You probably end up using them in industry anyway. So that brings us to the end. Happy to take questions if there are any. Hopefully that was worthwhile. It's given you a bit more of a practical understanding of how to use SolidWorks and some of the quirks of it. In my opinion, there's no point just going through the inbuilt SolidWorks tutorials because you don't actually learn all that much. I think having a bit more of a practical understanding of how it works and how you go about making a part is much more worthwhile. So thanks for coming.
Excuse me, Jack.
Yes.
You said something about the climbing hours with the website you shared. How much hours did you say?
So I